Good morning. Today we're going to talk about section 4.3 entitled the addition rule, and as we'll see, we use the addition rule when interested in assigning probabilities to OR type events. Let's talk about a motivating example first. Let's say 98 people take a lie detector test, perhaps as a condition of employment. And let me get some notation down here. I'm going to let L be the event that a randomly selected person lies during this lie detector test. I'm going to let not L, or the complement of L, be the event. I'll just say no lie. I'll let plus be the event of a positive lie detector test. In other words, the event that the machine detected a lie. So shorthand it like that. And I'll let negative indicate the event that the machine does not detect a lie from this randomly selected person. Detects no lie. Alright, so we got L bar, that's an L bar up there. Or not L, right? And plus and minus as indicated. Alright, I'm going to summarize the results of this lie detector test in a table type fashion. I'll make columns for the liars and the not liars, and rows for those found to be lying and those found to be not lying. And I'll fill in the numbers like so. Alright, so we've got liars and not liars cross-referenced, and those for which the lie detector found lies or not cross-referenced also. Alright, from this table, I will randomly select one individual from this pool of 98. And I'll ask, what's the probability that you picked a liar? Well, as we know, how many liars are there? There's 51 liars, right? As indicated in the table. The sum of those two numbers, those two cells, 42 and 9, that's going to be 51 total liars out of 98 total people, and that turns into a probability of 0.520. Okay? Alright, what's the probability? Again, randomly selecting one. I tried to circle that. Hang on a minute. Randomly selecting one person. What's the probability of getting someone for which the machine detected no lie? Well, the machine negatives are in that row that I just circled, and that adds up to 41 people whom the machine said did not lie. So I've got 41 negative test people divided by 98, and that turns into a 0.418 in decimal, right? Alright, what's the probability? Again, randomly select one. What's the probability of finding someone with a false positive test? And let's think for a minute. What does false positive mean? False positive means the machine said you lied, but you did not lie, right? So that would be this cell right here. Right? Notice in this cell, the machine said you lied, but you, in fact, you did not lie. The intersection of that row and column is 15. So we got 15 false positives divided by 98 total people, and we punch that out, we get 0.153. Alright. can similarly ask, what's the probability of a true negative? Randomly selecting a true negative test from these 98 subjects. Well, what does true negative mean? Well, that means you did not lie, and the machine said you did not lie. That would be this cell here. Scroll down a little bit. In this cell, the machine, or you in fact did not lie, and the machine said you did not lie, so that would be 32 people out of 98. Which decimalizes to 0.326. Alright, I want to invoke some OR events now. Let me define what OR means in a probability sense. OR. Well, probably the easiest way to visualize it is with what they call a Venn diagram. You've probably seen these before in your math careers. If this rectangle represents our sample space, our entire universe of available choices or available events, and let's say A is some subset of the sample space, and B, another event, another subspace of the sample space, I claim the probability of A or B is the probability of A, and we can interpret that as really the area of this circle in the Venn diagram, plus the probability of B, and we can again interpret that as the area of this B circle, but of course you're double counting this overlap, so I'm going to have to subtract the overlap, and I'll call that minus the probability of A and B, or the intersection of the two circles. Right? This, in fact, is our addition rule. Probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Or more simply, the sum of the individual probabilities minus the probability of the overlap. All right, let's go back to that lie detector test data. Doing the best I can freehand here. I can't really use a ruler with a tablet. Okay, we've got the no liars in this row, the liars in this row, the positive tests in this row, and the negative tests in this row. So 15, 42, 32, and 9. Again, we'll randomly select 1. And remember, the grand sum of all these subjects is still 98, same data as before. And I'll ask, what's the probability that you pick someone with a positive lie detector test or the event of lying? Alright, applying the addition rule, I could say it's the probability of a positive test plus the probability of finding a liar minus the probability of both. Okay? Well, what's the probability of a positive test? Well, we see we've got in this positive row, 42 plus 15 is going to be 57 positive tests out of 98 people, plus the probability of a liar. Well, let's see, in this column we've got all the liars, okay. So that's 42 plus 9, that's 51 over 98, minus the probability of both positive and liars. Well, we've double counted this cell if we add up that top row and the right column, so we've got to subtract off that overlap, namely minus 42 over 98. Alright, that grinds out to 66 over 98, and in decimal 0.673. Okay, let me put a box around that. Alright, please note I could have gotten there a little more informally, basically by adding these three cells I'm outlining in purple here. Right? 15 plus 42 plus 9 is going to be 66. 42, 57, yes, 66 over 9, and divide by 98, and arrive at the same value. Alright, so we can apply the addition rule formally in this type of situation, or perhaps a little more informally, realize that the sums of those three cells will indeed give us the numerator we desire, and hence the fraction 0.673. Alright, let's try another example. Let's see, I'm going to need another screen here, and let me quickly write down this data again. Positive test, negative test, 15, 42, 32, and 9. Let's see. Again, we randomly select one. Find the probability of a negative test or a not liar. And someone got a negative test or indeed did not lie. Alright, well, according to the addition rule, it's the probability of a negative test plus the probability of a not liar minus the probability of both. And all three of these values we get easily from the table. Alright, the probability of a negative test. Well, the negative tests are in this row here. 32 plus 9 is 41. 41 over 98 is that probability then. Plus the probability of not lying. Well, this row are the not liars. And then we've got 47 out of 98 probability to find a not liar. That's a 47 in the numerator. Minus the probability of both negative test and not liar. And of course, the intersection of that negative row and not liar column is 32. So subtract 32 over 98, and we can punch that out. We've got a numerator of 56 over 98, which grinds out to 0.571. And of course, we could have got there a little more informally by realizing, well, if we want not liars or negative tests, I really need to add these three cells, do I not? And divide by 98. So 15 plus 32 plus 9 is indeed 56 over 98, and we end up with the same answer. So if you want to apply the addition rule formally, or maybe more informally by viewing the table, that's okay too. Alright, disjoint events. You may have heard that term before. Disjoint events are otherwise known as mutually exclusive events, and that's a fancy way of saying they can't happen simultaneously. Write that down. Can't occur simultaneously. Alright? And perhaps easiest to visualize with a Venn diagram. If I've got a rectangle that represents our sample space, our universe of available events, if I've got some event A, which is disjoint to some event B, well, if they can't occur simultaneously, that means they share no possible outcomes, and in a Venn diagram that's represented by circles typically that do not intersect. And if A or B, A and B are disjoint, then of course the probability of A and B is by definition equal to 0. Well, if you consider joining A or B with an OR statement, then, well, the probability of A or B, according to the addition rule, is the probability of A plus the probability of B minus the probability of A and B. Well, if A and B are disjoint, that means this last term degenerates to 0, and the probability then of A or B is merely the sum of the individual probabilities. No overlap. Okay? Remember that for disjoint events. It gets a little easier if you can prove events are disjoint. What about complementary events? Well, again, not A is the complement of A, and typically referred to just in simple language, not A. Right? Some books say it's the complement of A a little more formally. Well, it kind of goes without saying, if we look at the Venn diagram of A and not A, I think you know where we're headed here. Again, a rectangle represents our sample space, our universe of available events. And if A is some body of sub-events, then not A, of course, is going to be everything outside of that circle A in our Venn diagram. Well, of course, either A or not A must occur, so the probability of A or not A equals 1. Because A and not A are disjoint, I can say then the probability of A plus the probability of not A equals 1. And what we're getting at here is that if I know two events are disjoint, I can find the probability of one if I know the probability of the other, because they have to add up to 1. So the probability of A is 1 minus the probability of not A if they are disjoint, and indeed they are, and the probability of A not A equals 1 minus the probability of A. Okay? Alright, so those three formulas involving complementary events. Alright, I want to do an example here. Get a fresh screen, I might run out of room. Alright. See page 155, and there is a body of problems in 155. This is the, check this, yes, it's your exercise set, basic problems and exercises at the very end of the section. And there's a body of problems referring to the same table, and I want to talk a little bit about that table. Alright, I'm not going to do all these here, but I'll pick one of them and grind it out for you and assign the rest for homework. Alright, I want to look at, let's see, let me read the little introduction to this body of problems here, right out of the text, again on page 155, right above number 33. In exercises 33 to 38, use these results from the one-panel THC test for marijuana use, which is provided by the company Drug Test Success. Alright, among 143 subjects with positive test results, there are 23 false positives. Among 157 negative results, there are 3 false negatives. Somewhat similar to the lie detector example. And they tell us, hint, construct a table similar to table 4-1, which is included with the chapter problem. Recall the chapter problem is always on the very first page of the chapter, and the text does refer to those chapter problems throughout each chapter or course. Alright, let me summarize what the book has just told us. We've got people undergoing a one-panel THC test for marijuana use, and it says 143 subjects test positive. That means the machine said that they used marijuana, right? And it tells us further there are 24 false positives. Write that down. 24 false positives. Okay? Alright, the book also tells us there are 157 negative results. They test negative for marijuana use. And of those, there are 3 false negatives. Okay? Alright, what I'm going to do is generate a table, much like that lie detector test table. And I'm going to let M be the event of marijuana use, and M bar, or not M, being the event of no marijuana use in any particular person. And then let plus and minus, as in the lie detector test, indicate what the machine said. Positive test meaning the machine found marijuana use, and negative test meaning the machine did not find marijuana use. Okay? Let's fill in the numbers here. You've got 143 that test positive, and 24 are a false positive. I claim that number goes in that cell. Right? Convince yourself, please, that's 24 false positives, meaning you did not use marijuana, but the machine said you did. Okay? Well, if there's 24 false positive, of course, this row has to add up to 143, because we know we have 143 total positive tests. So 119 must go in that cell. So using a little detective work, we can fill out this table. Similarly, in the second row, we've got 157 negative tests. So this bottom row must add up to 157. 3 are false negatives. That means you did use marijuana, or the candidate did use marijuana, but the machine said they did not. False negative, right? So that cell on the bottom row fills in with a 3, and of course the bottom row has to add up to 157. So that cell in the bottom row is 154. Alright, we're going to have to figure out some probabilities, so let me give you the grand sum. 300 people total involved in this test. And I want to work out number 34. Now, all these problems, 33 through 38, are somewhat similar. Let's take a look at number 34. Let me read it to you. I'm going to turn over the page. If one of the test subjects is randomly selected, find the probability that the subject tested positive or used marijuana. So again, randomly select one. Find the probability that the subject tested positive or used marijuana. Okay? Alright, and again, you can work this out either informally or formally. Let me do it a little more formally first. The probability of a positive result plus the probability of finding marijuana minus the probability of the intersection according to the addition rule. Right? Probability of positive plus the probability of marijuana minus the probability of positive and marijuana. Alright, what's the probability of a positive result? Well, how many positive results do we have? Total, there's 143, the sum of this positive row, right? Divided by 300, plus the probability of marijuana use. Well, that's the probability of this column, right? Or the sum of this column, really, divided by 300. So that would be 122 divided by 300 minus the probability of positive N marijuana. And of course, if we add this row and this column, we're double counting the 119, so we're going to subtract off 119 over 300. Alright, all these fractions have the same denominator. That's nice. So all I need to do is add or subtract the numerators as indicated. I get 146 divided by 300, the result of 0.487. Alright, so there's my probability. Of course, a little more informally, I could have realized, well, if I want the probability of positive or used marijuana, all I really need to do is add those three cells and divide by 300, right? So let me work it out again a little more informally. Probability of positive or marijuana, it's going to be 24 plus 119 plus 3 divided by 300, and hang on a minute. I've got 24 plus 119 plus 3 equals 146 over 300. That's a 6 there. And of course, I get the same answer I got with a little more formal approach here. Okay? Same correct answer. Alright, one note before we call it a day is that exercises 17 through 20 are similar to exercises 33 through 38, but they refer to a different table. They refer to table 4-1. And table 4-1 is stated in the chapter problem, that chapter problem that always exists on the very first page of each chapter, and in this chapter it's page 133. Right, so you'll need to refer to that table to complete homework exercises 17 through 20. Alright, we'll call it a day. This concludes section 4.3 video lecture.